Hello everyone, welcome to the first video lecture on communication networks and transmission lines. So in this lecture we will be seeing some introduction. So we will be reviewing what is a network, what are the various types of network like filters, attenuators, etc. Then we will move to network elements, that is the various types of network elements. We have already heard about linear elements, non-linear elements, active bilateral elements, etc. So we will be seeing examples for each of these. Then we will have a quick revision of the two-port networks, a quick review of the various parameters, parameters of two-port networks. Then we will have an introduction to what is a symmetrical versus asymmetrical network. So we will try to understand this with respect to a T network, a pi network, then we will see what is a lattice network, etc. Then we will see one special network which is an asymmetrical network, which is an L network, and half sections. So this course is divided into 5 units. Okay. So in unit 1 we'll be focusing on certain characteristic parameters of symmetrical and asymmetrical two-port networks. So characteristic parameters symmetrical and asymmetrical two-port network. So in a previous course, network analysis and synthesis, you might have been introduced to two-port networks. You might have analyzed that. So this course is like a continuation of that course. Also, we will be seeing some of the symmetrical and asymmetrical networks once again. We will be revisiting them. Networks such lambda parameter equivalent networks such as T network, pi network, and some special networks such as lattice network, bridged T network, etc. So after that we'll be seeing some of the parameters for symmetrical networks. So they are characteristic impedance, and propagation constant. Then for asymmetrical networks, we will be seeing parameters such as image impedance, iterative impedance, image transfer constant, or coefficient, iterative transfer constant or coefficient. So after this, we'll be seeing some special applications like matching networks, attenuators, plus their design. Okay. In unit 2, we'll be seeing on filters and their design, basically passive filters. Okay, so we'll see passive LC filters, RC filters, plus their design. Also, we'll be seeing some approximations such as Butterworth, approximation, so we'll be discussing basically the drawbacks of these filters, then how we can overcome those drawbacks by these approximations. Also, we will be seeing another approximation from these basic filter networks, which we can call as M-derived filters. In unit 3, we will be gradually moving towards network synthesis. So we'll be seeing what is a positive real function, or in short PRF. Then how we can synthesize some basic LC, RC, RLC networks given the network function. Okay, so some methods like Foster, Coyer, Ronis, some mathematical methods are available like this. Foster's first form, Coyer first form, like that. So we'll see how these vary, how these network synthesis methods are going to vary, what are its layout, like that. Then moving towards unit 4, so we'll be introduced to transmission lines. So we'll be seeing the lambda parameter equivalent of these transmission lines. We know that transmission lines are distributed, so how we can approximate it in the lambda parameter equivalent model. So again, we will be discussing on parameters like characteristic impedance, propagation constant, etc. Also, we will be seeing reflection factors, reflection losses, insertion loss, etc. So unit 5 is continuation of this, in which we will be analyzing transmission line at radio frequencies. Because we are interested in radio communication, so what are the parameters of these transmission lines at high frequencies that are used for communication, not the power frequency, which is used for power transmission. And we see some equivalents like 8-wave, quarter wave, half wave line, etc. Then we'll be introducing to circle diagrams and Smith chart. Half wave lines and circle diagram, Smith chart. So with that we will conclude this course. Now few of the references that are mentioned in the syllabus are networks and transmission lines by writer. Then you can refer Introduction to Modern Network Synthesis. Falkenberg. A few more references are also mentioned in the syllabus. You can refer them. So we'll start with the introduction by trying to understand some of the basic terms like network. So we are interested in an electrical network. So we can define an electrical network as an interconnection of electrical elements that perform a specific function. So what are these electrical elements? Examples are resistors, inductors, and capacitors. Some of the electrical elements that we know, passive elements. We can also have certain active elements also, like semiconductor devices. Also in this course, we are basically interested in 4 major types of networks. So we can define certain types of networks. Okay, so what are those network types? First category we can call as filters. Actually, filters are frequency selection networks. So you must be knowing about low pass filter, high pass filter, band pass filter, band elimination filter, etc. So depending on what frequency this network is selecting, you can categorize filters like that. Second category of networks are attenuators. So actually filters are also having attenuators built in within them, in the sense that it is not giving any attenuation to a selected frequency, whereas it is giving maximum attenuation to certain other frequencies. Whereas attenuators are exclusively for power dissipation applications. Okay, so networks used for that. Okay, power dissipation. For example, in speaker volume control, so you'll be controlling the volume by means of a knob. So actually we are adjusting the parameters of attenuator there. Another example I can give you is related to antenna. So we have amplifying circuits and the output is connected to an antenna. So in order to control the power that is being radiated, we use attenuators just before the antenna for certain regulation purposes. Third category of networks are equalizers. So they are power compensation networks. So basically to control the active and reactive power, we can use inductors, capacitors, etc. Okay. The fourth type are matching networks. They are basically used for impedance matching. Impedance matching between the generator and load. So why we need impedance matching? Impedance matching is required to eliminate reflection. So what is the advantage of eliminating reflection? It is done to maximize the power transfer. Okay, the power that is being transferred from the generator or the source to the load. Okay, next let us recollect some of the network elements. So we broadly divide or classify network elements into one kind of classification is called linear elements. Resistor, inductor, etc. So what is the specialty of linear elements? These elements have the property that the electrical parameters by parameters we mean the properties of the network elements. For example, resistors have resistance, inductors have inductance. Okay, so electrical parameters are like resistance, inductance, capacitance, etc. Okay, so for linear elements, these parameters of these elements do not change with the applied voltage. Do not change with the applied voltage. So it means that Ohm's law is obeyed. That is, we apply a voltage V, then we will get a current I that is proportional to the voltage applied. So when we apply a different voltage, for example, if we take a resistor, having a resistance value R, and we apply a voltage V across this. Current, say I, is going to flow. So as we linearly increase the voltage V, I is going to linearly increase. R is not going to change because resistor R is a linear element. Okay, R value will not change as we vary the voltage V. So when we plot the variation of V against I, we will get a straight line with a constant slope, and the slope of this line, or 1 by slope of this line, will be the resistance value. Okay, so delta I is delta I. This is the slope. So this takes us to another category of elements, which is non-linear elements. Okay, so if linear elements are like, the electrical parameters of these elements do not change the applied voltage, so the definition for non-linear elements will be like, the electrical parameters of these elements are going to change with the applied voltage. Okay, so the electrical parameters of these electrical elements or network elements going to change with the applied voltage. Change with the applied voltage. So what example can you give? All semiconductor devices we can give. So for example, we will take the case of a diode. So simplest semiconductor device that we can consider, PN junction diode. Let's see the forward bias condition. We are applying a voltage V across this diode. So forward bias means the current should flow in this direction. Okay. Higher polarity, lower polarity in this side. Okay. We are interested right now only in the forward bias condition. So we have already studied in an earlier course what will be the shape of this graph. So we can define, for example, a semiconductor device. We can define a cut-in voltage or a new voltage at 0.7 volt for silicon and 0.3 volt for germanium, after which we can see that the diode is offering higher resistance than the non-linear region. I'm just going to we get, once the diode is on, we get a linear region. So we are applying a small voltage here. It's the dynamic region. So here at every point the resistance is going to vary as we change the applied voltage. But here, once the diode is started conducting, we get a constant resistance. Okay. But since this is, you cannot write an equation like V is not proportional to I. Write an equation like this. So this is a non-linear graph as compared to this graph, straight line graph, starting from the origin. So another classification of network elements is active versus passive elements. So what is an active element? So an active element are capable of, these elements are capable of enhancing the power level or energy level of the signal. Power / energy level of the signal. So examples are like vacuum tubes, now not used, transistors have replaced them, batteries, etc. So what are passive elements? So these passive elements are incapable of enhancing or boosting the power or energy level of the signal. Example for passive devices are resistors, inductors, capacitors, thermistors, etc. Semiconductor device. Another category of network elements are unilateral and bilateral elements. So what is a unilateral element? We can define unilateral elements as those such that magnitude of the current through these elements are going to depend on the polarity of the applied voltage. Examples include diode, transistors, etc. So what is the meaning of this? We'll take the case of a diode. A simple example of that of a diode. It's a unilateral element. So in an earlier course you must have studied about the forward bias and the reverse bias characteristics of a p-n junction diode. So we have already drawn the positive characteristic. It's a shape like this. So dynamic region, nonlinear region combined with the linear region, the resistive region. So this is the current. For example, we are applying particular voltage, say for example I am applying a voltage, say V1 plus V1. So what is plus V1? Plus V1 is in the positive direction. Okay, like this. This side is positive and this side is negative, that is plus region. And for this particular voltage I get this current. So I get current I1 corresponding to this. Okay. The positive direction. Now I reverse this voltage. Same magnitude but in the reverse manner. That is, here positive will come and here minus will come. This is reverse biased. So what is shape? Is the reverse bias characteristic. So the diode is in non-conducting mode. The only current is a minority carried current we can get. And when we go beyond the breakdown voltage, we can see the diode is getting, current is increasing, the breakdown region. So the same voltage V1 applied in the negative direction. So voltage is minus V1. What's the current we are getting? Magnitude of the current we are getting is this much. It's a different current. So I1 dash. So magnitude of this current is different from the magnitude of this current. So diode is an example for a unilateral element because the magnitude of current through this element is going to depend on the polarity of the applied voltage. You apply a positive voltage, you get a magnitude of current having this much magnitude. Now you reverse the polarity of the applied voltage, like this, same magnitude but in reverse polarity. What happens to the magnitude of the current? It is different. So I1 dash here. Okay. So this is an example for a unilateral element. So this takes us to the definition of a bilateral element so that takes us to the definition of a bilateral element. So the definition is pretty straightforward. The magnitude of current through these elements do not depend on the polarity of the applied voltage. Examples we can write: resistors, inductors, capacitors, etc. So let's take the case of a resistor, simple resistor. We know that it is going to obey the Ohm's law. So what is the shape of the, apply a positive voltage, you can see current is going to increase linear manner. You reverse the voltage, you can see the current is going to increase in linear manner in the opposite direction, passing through the origin. Apply a zero voltage, current is zero. So we apply a voltage, say V1, across this resistor, say R. So applied voltage V. So this is a positive direction, plus minus. Applying a positive voltage V1, we get a current. This current, this is the current. So I1 having this much magnitude, but in this direction, positive direction. Now you reverse this voltage, same voltage, the reverse polarity. Okay. So this is again V1, but in the reverse direction. Okay. Minus V1. Again you get a current, which is I1. Okay. Current direction will be changing, but the magnitude of this current will be the same as this current. That is the current that we obtain when we apply a positive polarity voltage V1. When you reverse the polarity V1, the current direction will change, however the magnitude is going to remain the same. But this was not the case of a unilateral element. When you apply positive voltage V1, current was this much, of the order of milliampere. Because when you applied a reverse polarity V1, same magnitude as this, but we get a small current of the order of microamps only. This is reverse biased diode. Now we see a technical term called distributed network. So what is a distributed network? Okay. So we can define a distributed network as a network in which the network elements so what are these network elements? Resistors, inductors, capacitors, etc. Such elements are distributed uniformly over the entire network. So where can you see such distributed networks? You can see that in transmission lines. Both power transmission lines as well as signal transmission lines. So these transmission lines are stretching over several kilometers. So these have got resistance, inductance, capacitance, etc. that is getting stretched or distributed over several kilometers like that. Cables, signal cables or power cables, etc. So the analysis of these distributed networks becomes little complicated. So we normally try to approximate to its lumped parameter equivalent. Also we can see certain Lambda networks like filters, etc. So what is a Lambda network? A network in which the network elements are lumped. So what is lumped? Lumped means they are together, clubbed together, so that we can physically separate them. That is, they are physically separable or separate. For example, when we move to filter design, those circuits will be placing certain, for example, in RC filters we will have some resistors, capacitors, etc. Separate resistors, capacitors, etc. Similarly, matching networks, etc. Okay. So we have individual capacitors, resistors, inductors, etc. in Lambda network. Next, let us take a review of a two-port network. Another name is four-terminal network. So you must have already introduction to this. So any network could be represented by a box like this with two input terminals and two output terminals. Okay. So we'll label this input terminals as 1 dash, output terminals as 2 dash. So this is called the input port, and this is called the output port. Another name is the sending end, and this is the receiving end. So here we have the generator or the signal source, and the power is transmitted through this network transmission line, or the signal gets transmitted through this network of transmission line, and at the destination or the receiver we get the power. So Vs is the sending end voltage and Is is the sending end current. At the receiver end we have a different voltage Vr and current IR, the received current. So why we represent a network like this is basically for analysis purpose. So sending end, so receiving end. So we can define various parameters for this. If you must be have been introduced in your previous course in network analysis, in which you must have analyzed two-port network. So this is like a review on that. But before we start on that, let's see how many parameters could be defined for a network like this. That is for a four-terminal network. That is a two-port network. So the answer is 6. You can define 6 parameters. So there's a general expression for that. For example, if there are n number of ports for an n port network, we can define two n factorial upon n factorial square number of parameters. So for a two-port network, n is equal to 2. So how many parameters can we define? We can define 2 into 2 factorial on 2 factorial square number of parameters. So what is this? This is 4 factorial divided by 2 factorial is 2 it is 4 whole square. So this is 3 into 2 into 1. So we can have 6 parameters. So what are those parameters? We can have an open circuit impedance parameter or the Z parameter, and the short circuit admittance parameter or the Y parameter. These two are the most commonly used parameters. Then we can have special parameters like ABCD parameters, or another name is transmission line parameters. Another name is chain parameters. In short, we can tell T parameter, transmission line parameter, and the inverse transmission parameters, or in short T dash parameters. So 4 parameters. The 5th parameter is the hybrid parameters or the H parameters. You may be familiar with this. And the inverse hybrid or the G parameters, the 6th one. So these parameters are basically used for analysis of electronic circuits. For example, we must have studied about the H parameters of transistors of a BJT like that. These ABCD parameters are actually used for analysis of transmission lines and networks. So this course will be focusing more on these ABCD parameters as well as the OC and SC parameters, Z parameter and Y parameter. This is for electronic analysis. So we have defined what is a two-port network and why we represent a network using two-port network. It's basically for analysis purposes. Okay. For easily studying this, we can represent a network like this. So we know certain parameters, we can find out certain other unknown parameters, provided we know these parameters of this particular network. So these 6 parameters are defined for this box. So once the network parameters are known and we apply some voltage at the sending end with some sending end current, we will be able to determine what is other 2 parameters like that. So those were the basics introduction. Now we move on to our unit 1. Actually, we are going to enter into symmetrical networks and asymmetrical networks. So first, let's have an understanding of symmetrical networks. So how can we define a symmetrical network? So for a network to be symmetrical, condition is that the electrical parameters of these networks are unaffected by interchanging the input and output terminals. For example, we have a network, a symmetrical network, symmetrical two-port network, symmetrical network, and let us say these are the input terminals, these are the output terminals, and we apply a voltage, say V1 here, and we get a current I1. You take the ratio V1 by I1, it will have a particular value, and now you apply the same voltage V1 to the output side, and you get a current having, say, I dash is equal to I1, so that the parameters like V1 by I1 will be the same as V1 by I dash. This way we can check whether the circuit is symmetrical or not. Now coming to asymmetrical network, it's opposite of this, the opposite of that. The electrical parameters of asymmetrical networks change if the input and output terminals are interchanged. So we'll explain this when we discuss on T networks. Next we shall see some of the network configurations that we can use for analysis purpose. So we'll see some network configurations. So the most popular ones are T network, and the pi network. Okay, so we'll start with the T network. So it has a typical structure. So a T network has a typical structure of the form like T. So you can draw like a T. See, the network elements are lumped like this: Z1, Z2, Z3. Join this. so that it will look like the form of a two-port network, input port and output port. So we label these terminals as 1 dash and 2 dash. When will this network be symmetrical? So this network will be symmetrical if Z1 is equal to Z2, sorry, Z3. Z1 is equal to Z3. Okay, and this network will be asymmetrical when Z1 not equal to Z3. So how do we verify this? Okay, how do we verify this? You can put some numbers. For example, when Z1 is equal to Z3, say we take the case when Z1 is equal to Z3. Let's take a very simple example like this is 1 ohm, this 1 ohm, this is 2 ohm. So when we look at the input side, we can see that the input impedance, which is equal to 3 ohm. Okay, that's when we look from 1 dash. When we look from the output side 2 dash, you can write an impedance of this 1 ohm series with this 2 ohm, this is 3 ohm. So how we have defined a symmetrical network? Electrical parameters of these networks are unaffected by interchanging the input and output terminals. So we will apply a voltage V1. Okay, and we will apply the same voltage V2, sorry, V1 at the output side also, second terminal also. If we are able to prove this, that this ratio is the same voltage is applied to the input as well as the output terminal, then this network is symmetrical network. So here we can readily see that Z1, what is this Z1? The same as we apply a voltage here across this terminal and say I1 is the current, then Z1 is this ratio V1 by I1. Similarly, we apply voltage V2 here, sorry, the same voltage V1 here, since Z1 is equal to Z2, what will be is I dash, it will be same as I1. So we can prove that V1 by I1 is equal to V1 by I dash, which is equal to 3 ohm. So this is a symmetrical network. Now what if the series branch impedances are not equal? That is, this case Z1 not equal to Z3. Now the network becomes asymmetrical. How? For example, we take this as 1 ohm, this is 2 ohm, this is 3 ohm. So what is Z1? Just 1 series with 3, this is 4 ohm. What is Z2? 2 series with 3, 5 ohm. So if we apply a voltage V1 here, and we observe the current I1, so what will be I1? It will be V1 by Z1 is equal to V1 by 4, and we apply the same voltage V1 here. We observe the current I dash. So what is I dash? Is equal to V1 by Z2. This is equal to V1 by 5. So we can prove I1 not equal to I dash. So can we write an equation like this? So V1 by I1 will not be equal to V1 by I dash, since I1 not equal to I dash. So this proves that this is an asymmetrical network as per the definition that we have written. That is, electrical parameters of these networks change if the input and output terminals are interchanged. Electrical parameter. Here we are considering the parameter, which is the impedance parameter, that is Z1 and Z2 of a T network. Another popular network configuration is the pi network configuration. So we can have the branch elements shape of a pi. As shown. Okay. Let's label the network elements. This is impedance ZA, ZB and ZC. So 1 dash, 2 dash. So this network is symmetrical if the shunt arm impedances are equal. Okay, there is no role for the series arm impedance ZA. Symmetrical if ZB is equal to ZC, and this network will be asymmetrical if ZB not equal to ZC. This you can prove using similar lines that we have used for proving T network. Actually, this is like a delta. This point is the same. So we can represent this network like this. Actually, these points are same. Branches are terminated like this. What is this point? This is this point. this point, this is point 2. This point is a common point, 1 dash, this point 1 dash 2 dash. It's combined together as a common point, common to both the input as well as the output side. Now if we take the T network and observe it, this is like a Y or a star network. Okay, so from point 1 and in between Z1 and Z3 we have an intermediate point, and Z3 is terminated at terminal 2. So we can start drawing from 1 and we will get an intermediate point, and this is Z1. And from the intermediate point, Z3 is going to terminal 2. So Z2. Okay, so this is intermediate terminal. From there this is Z3. Okay, from the junction point of Z1 and Z3 we have Z2 starting. And where is Z2 going? Is going to the common terminal 1 dash and 2 dash as shown here. So why this is drawn? This is drawn to show that we can convert from a T network to a pi network, or a pi network to a T network. So pi network, that is delta star transformation, which we have already derived in an earlier class. So using the delta star transformation we can write this delta could be converted to the star. For example, we can write for Z1 is equal to ZA ZB on ZA plus ZB plus ZC. In short, we can write this is as ZA ZB divided by sigma ZA, where sigma ZA is sum total of the impedances ZA plus ZB plus ZC. Similarly, we can write Z2 is equal to ZB into ZC, ZB ZC upon sigma ZA, where sigma ZA is again ZA plus ZB plus ZC, and we can write Z3 is equal to ZA ZC upon sigma ZA. Okay. Similarly, we can use the reverse transformation, that is star delta transformation, to find the delta parameters. For example, we can write ZA. How we can find ZA? ZA is equal to Z1 Z2 into Z2 Z3 into Z3 Z1 divided by the opposite branch impedance Z2. So ZA is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1 divided by opposite branch, that is Z2. Or in short, we can write this as sigma Z1 Z2 divided by Z2. Similarly, we can write ZB is equal to sigma Z1 Z2 divided by ZB. So it should be Z3, and ZC is equal to sigma Z1 Z2 divided by Z1, where sigma Z1 Z2 is equal to Z1 Z2 plus Z2 Z3 plus Z3 Z1. Okay. We have already studied this in your earlier courses. Now, what is the relevance of this T and pi networks? They are basically used for transmission line analysis, that is for the lumped equivalent representation of transmission lines. Okay. So for easily understanding, we know that transmission line is an example for distributed network. So we have to approximate this short and medium transmission line in terms of T and pi networks for easy analysis. Okay. Okay, so we have seen the first two network configuration, that is the T and pi networks, which can be used for representation of transmission lines for analysis purposes. The third network configuration is a lattice network. Represent this in the shape. So these are the series arm impedances, which we can represent as ZS1 and ZS2. And these are called the diagonal arms, which we can label as ZD1 and ZD2. So such network configuration is used for basically digital filters. That is a lattice network. So when this network will become symmetrical, we can answer this question after we draw an equivalent network for this. So we can draw an equivalent network for this lattice network. So we have the input terminal 1 dash, one dash. So from 1 two branches are splitting. So one is going to terminal 2, the output side, through Z1, ZS1. So through ZS1 is going to reach terminal 2, and from this point another one going to is a D1, the diagonal element, which is going to is 2 dash, terminal 2 dash. Similarly, from 1 dash, one of the element is going to 2 dash, so which is that element, this one. So this should be ZS2, the series arm element. So automatically this will be the diagonal arm element, is going towards the terminal 2. So this should be ZD2, the diagonal element is D2. So now the picture becomes more clear. So when will this become symmetrical? So this will become symmetrical. So we have to see the input impedance like this. So this will be in series, and these are in parallel. And the output impedance again, this will be in series, and these two are in parallel. So the condition for this network to become symmetrical is only one ZS1 is equal to ZS2 and ZD1 is equal to ZD2. Both should be true. Only it will become symmetrical. If either of these are not equal, then the network will not be symmetrical. It will become asymmetrical network, asymmetrical lattice network. So asymmetrical, this lattice network will become asymmetrical if ZS1 is not equal to ZS2, or logical or ZD1 not equal to ZD2. So both these conditions should become true for this network to become symmetrical. So what is the application of lattice network? It is for filter networks. Okay. So T and pi networks are used for transmission line analysis. Lattice network is for filter representation, for designing filter networks, digital filters. So coming to the third network configuration, it is the bridged T network. So this has the shape like that of T. A normal T you can draw. We can label this as Z1, Z2 and Z3, and there will be a bridge from 1 to 2, So this we can label as Z4. So the condition for symmetry is the same as that for a T network. That is when Z1, that is the series arm impedances should be equal, and it will become equal. It will be this network will be asymmetrical when the series arm impedances are not equal. Okay, Z1 not equal to Z2. Z3 and Z4 have no role to determine the symmetry of this network. Fourth category is the twin T network. So we have two T networks. And one more T network we can draw. So yesterday ZB and this will be ZC dash and 2 dash. So what should be the condition for symmetry? Z1 should be equal to Z2 and ZA should be equal to ZB. So application is used for notch filters. Designing notch filters. That is for eliminating a certain small, very narrow band of frequency. And for a bridge T network is generally used for filter networks and equalizer networks. Okay, so applications include, they are used in filter networks and equalizer, that is power compensation, equalizer networks. Okay. 20 is used for design of notch filters. We'll see this when we come to unit 2. Okay, another network configuration is an L network. So it's basically going to look like, we can represent like an L shape. So this is the series arm impedance. The shunt arm impedance is a drop. As you can see, this is like a special case of a T network. When the series arm impedance, this impedance become equal to 0. So this is basically an asymmetrical network. Also, one can view this as a special case of a pi network also. So this is a asymmetrical network. Example for an asymmetrical network. So we have a T network like this. So this is Z1, Z2, and when Z3 is equal to 0, then this will disappear. So it will become like that. An L network. Special case of a T network. Similarly, if we consider a pi network, like this. Okay. This is Z1, Z1, and this is Z2. Okay. Say this is Z3, and this is an open circuit. That means Z3 is equal to infinity. Then this will vanish. This thing will not be there. This branch will be an open circuit. So this pi network can be transformed to an L network. So this L network can be viewed as a special case of a pi network also, when this shunt arm impedance is equal to infinity. Similarly, an L network can be visualized as or viewed as the special case of a T network, and this series arm, one of the series arm impedance is equal to 0. The application is for matching networks. L networks are used for matching circuits. Okay, because we are having a particular impedance when we view from this side, right? So Z1 or ZI from the input side, see that impedance is equal to Z1 plus Z2. You look from this side, Z0 is equal to Z2 only. So unequal impedances on the input as well as the output side. So this can match these two kind of networks. Another category is half section. So we can have half sections for a T network. For a T network, Z1, Z2, and Z3, 1 dash, 2 dash. So how can we split this network into two halves? So we have to split along the shunt arm. There is no change going to happen for Z1 and Z2. So we can represent this T network as an equivalent half section. How? Let us split this Z3. How can we split Z3? The shunt. So we draw Z3, split like this. Okay. Z1, Z2. Split it like this. So this has to be equal to twice of Z3, to twice of Z3. So that when we combine this parallel this will be equal to half of 2Z3, that will be equal to Z3. Okay. Similarly, so for a pi network, also we can have a half section like this. So this is ZA, ZB and ZC, 1 dash, 2, 2 dash. So we have to split along the series arm. So how will be the equivalent half section? So we have the first rundown message, this is not disturbed, and we split the series arm into two impedances, and the shunt arm impedance ZC on the output side is also not getting changed. So we have 1 1 dash, 2 2 dash. So this is ZC. ZA is split into two halves. So when we combine this half section, it should become equal to ZA. So it's in series combination. So what should be? So it has to be ZA by 2. This should be equal to ZA by 2. So that when we combine this will be ZA by 2 plus ZA by 2. That will be equal to ZA. So you will get back the original pi network. Whereas for T network, we split the shunt arm. So the net impedance Z3 is actually the parallel combination of 2 Z3. Okay. Another possible combination is a combination of all these networks that we have already discussed. Or we can have a cascaded or recurrent or a ladder network. So we can connect any of these networks that we have discussed so far in a cascaded manner. For example, we can have a cascading of T network like this. One section, another T network like this. Cascaded. Like this it can go on. So that is a T network that is cascaded. Or you can have a cascading of pi network. Like I have one pi network here. I have one pi network here. Then it's cascaded with another pi network like this. Okay, like this it can go. So this is cascade network. Again, if you can look, this is like a half section. Up to here, if you look, this is like a half section of a pi network. Actually, it is a cascading of T network, but here, if you check this. Similarly, if you see here, up to here, it's like a half section of a pi network. Sorry, T network. Half section of a T network. Actually, it is a cascaded pi network. Okay. So with that, we are concluding this introduction section. So in this lecture, we have seen some of basic introduction, that is review of what is network elements, etc. Then we have seen network types, like what is a specialty of filters, matching networks, equalizer networks, etc. Then we moved to the review of two-port networks, like how many parameters we can define for an n-port network. From that we have started, and we have understood the application of an ABCD parameter or the transition line parameter. Then we have defined what is a symmetrical network and asymmetrical network. How we can test whether this network is symmetrical or asymmetrical with respect to T network. We have seen the example. Then we have seen some network configurations like T network, pi network, lattice network, bridge T, twin T, etc. and their applications, why these networks are used. So we are focusing mostly on T and pi networks for transition lines, and when we move to filter design, we will see other networks such as lattice networks, etc. Then we have visited asymmetrical network, which is the L network, and we have seen how we can view a T network or a pi network as its equivalent half sections. Okay, with that we conclude this lecture 1. Lecture 2 we will be discussing on characteristic parameters of symmetrical as well as asymmetrical networks. Okay, thank you.